Last time we looked at electrical potential, also known as voltage, and current. Today we want to look at resistance and an equation we're going to develop that's known as Ohm's Law. A little quick review on electrical current. If you have a wire and electrons moving through that wire, current is how many charges go by every second. And charges are measured in coulombs per second, also known as amps. Amp would be the common unit, the one-word unit. So an equation to calculate that, we use I for the intensity of the current, Q for the quantity of the charge, so it's just how many charges go by every second. And it was named after Andre Ampere. Now, in my animation, I showed electrons moving to the right, but we have conventional current. It says it's the flow of positive charge. So if electrons move to the right or protons move to the left, we would say the current was moving to the left. And then electrical potential, also known as voltage. You can give charges energy by pushing them to where they don't want to go, or by separating them from where they do want to go. That's like charges repel and opposites attract, but when you do work on them, you give them energy. And voltage is how much energy there is per coulomb of charge. The unit is volts, named after Alessandro Volta. And then we have this equation is basically the same thing as the units here. U is an abbreviation we use for potential, and this is electrical potential energy. And if I just take the amount of electrical potential energy available divided by how much charge there is, that would be the voltage. We often say it's the difference in the potential. All right, so let's say that we have two situations here where we have a bunch of negative charges pushed very tightly together, and same thing for the positive. This would represent a high voltage. And down here, the electrons are not pushed together quite as tightly. It didn't take quite as much work to get them to where they are, but they're connected by a wire. And maybe it's not surprising that because these are so pushed together and they don't want to be there and they really want to be over there, when you connect it with a wire here, current is going to flow, but more current is going to flow through that wire when there's a higher voltage, a difference in potential from one side of that wire to the other. So these two things are going to be directly proportional. If I had half as much voltage, I should have half as much current, as long as everything else about that is the same. So voltage and current are directly proportional. This is the symbol for proportional. And if two things are directly proportional, you can set them equal if you multiply by the right proportionality constant. So in this situation, the voltage was the same, but we had a different wire connecting those two. This wire may have been made out of copper, and this wire may have been made out of aluminum or something. But we had a higher current running through this wire, which a larger current means that proportionality constant must have been smaller, because a big number times a small number can equal the same number as a small number times a big number. So there wasn't as much current running through there. That means that proportionality constant must have been larger. So if voltage and current are proportional with this proportionality constant, you can find out what that constant is by taking voltage and dividing by current. And what does that proportionality constant mean? It is the resistance of that wire, or the thing connecting the positive and the negative. And then we can look at the units of that. Now, resistance kind of seems like friction, and it's not bad to think about it that way, but we have to understand that electrical resistance, the units are not newtons. It's not an actual force, it's just a ratio of those two terms. So to look at the units of resistance, we have to take the units of voltage and divide it by the units of current. So voltage is energy per charge, current is how many charges go by every second, fraction over a fraction, you copy dot flop, and you would get these units here. Joule seconds per Coulomb squared. And that does have a common unit, and the unit is ohms, named after Georg Ohm. So ohms is the unit of resistance, and then we symbolize it with this Greek letter omega. Now, we have used the letter omega earlier in physics, but that was a lowercase omega, and that was for angular velocity. So we have these three people here. We've got Alessandro Volta, Andre Ampere, and Georg Ohm. It doesn't look like it, but they are related of sorts. They're related in this way here, that voltage is equal to current times this proportionality constant that we call resistance. We say V equals IR. V for voltage, I for current, R for resistance. That equation is known as Ohm's Law. And we often see that rearranged like this, solved for the current. So the current that we get running through a wire is going to be equal to the potential difference on either side of that wire divided by the resistance of that wire. So if I had a toaster oven here and you plug that toaster oven into the wall, which is 120 volts, you're going to get current running through that wire. But you don't want too much current running through that wire. You can also get the current running through these wires, and these wires can get too hot and catch your house on fire. So a simple plug and chug problem here. What minimum resistance is needed for this toaster filament so that the current doesn't exceed 10 amps? Well, it is just plug and chug. The voltage was 120 volts. We want to have it no more than 10 amps of current. So we solve for the resistance, multiply both sides by R, divide both sides by 10. We get R by itself, and 120 divided by 10. As long as we have 12 ohms of resistance in that wire, you won't get more than 10 amps when you plug it into 120 volts. Now, there are two kinds of resistors, or two classes of resistors. One would be ohmic, and the other is non-ohmic. And ohmic resistors simply follow Ohm's law, that voltage and current are directly proportional. So if you graph those two, you should get a straight line here. Now, if we graph voltage on the x-axis and current on the y-axis, the slope of that line is going to be 1 over the resistance. So an ohmic resistor, if I had this voltage and I got that much current, if I doubled the voltage, I would also double the current. But other resistors don't behave quite like that. That as we get more and more voltage, the current does increase, but it doesn't increase linearly. You can see the slope here is smaller than what the slope was here. And if slope is equal to 1 over the resistance, that must mean that the smaller slope had a bigger resistance. So as we put more and more voltage on this thing and got more current, the resistance increased. And why would that be? Well, if you have a wire or something like a filament of a light bulb, and you put more voltage on there, more current causes that filament to heat up. And the atoms that make up that filament jiggle around a lot faster, knocking the electrons back and forth, so the electrons are not as free to flow through that filament. So this would be a non-ohmic one, that the higher voltage increased the current, but it increased the temperature. So there was actually more resistance at this voltage than there was at this voltage. And an example of that, here is a set of light bulbs connected to a power supply. I have my alligator clips on either side of that light bulb, so I'm measuring the potential difference from one side to the other with this one, and the voltage was, or the potential difference was 4.05 volts. Whatever current runs through this bulb is being diverted through this multimeter and converted back to here, so this is measuring amps. V equals IR, the voltage was 4.05 volts, current 0.23 amps. Solve for the resistance, and I get 18 ohms. That'd be the resistance of that light bulb there. Now, if I had unscrewed that light bulb and let it cool down and then set my multimeter to measure its resistance, I would have gotten a resistance a lot less than that. And that's because that extra heat of it glowing red hot there gave it more resistance than if it was cool. A light bulb filament is non-ohmic. All right, so one point of confusion perhaps is if we have these variables here and we want to just kind of make sure we have it all square in our head. So we have these three concepts: voltage, current, and resistance. The symbol for the concept voltage is just the letter V. That's nice. Its units is how much energy there is per charge, joules per coulomb. And the one-word unit that represents that is volts. And nice enough, we also abbreviate volts with a V. For current, we use the letter I, and that seems a little funny, but it stands for the intensity of the current. And it's how many charges go by every second, coulombs per second. The one-word unit for current is amps. This is the the common unit. And we use an A to abbreviate amps. Resistance is R. Resistance is the voltage divided by the current. So we take these units divided by those units and we get those crazy units, joule seconds per coulomb squared. And the common unit is ohms, abbreviated with the capital letter omega for O. So if I say V equals 12V, this is not an algebraic equation to solve. What I'm saying is the voltage was 12 volts. If I say I equals 4A, I'm saying the current was 4 amps. And if I say R equals 3 omega, I'm saying that the resistance was 3 ohms. And we do see the Ohm's law applies here, that the voltage is equal to the current times the resistance. Another equation we can develop, and it should make sense, this is not just magical and mysterious, but if we look at the units of this equation, hopefully it will make sense. Power was how quickly we did work. It was measured in watts. Voltage is how much energy there is per charge. Current is how many charges go by every second. So if I have a certain number of joules per coulomb, and then I figure out how many coulombs are going by every second, coulombs are going to cancel, and it's going to be how much energy is used every second, which is watts. So if I take like a 3.5 watt LED bulb, plug it into 120 volts, how much current is going to be running through that? And it's going to be about 0.113 amps. So power is equal to voltage times current. That's another equation that we could look at. And this just follows as a result of that. It follows by taking Ohm's law, V equals IR, plugging in right here IR, multiplying by I, and we get I squared R. So we can look at the units. Because current gets squared, we have coulomb squared per second squared, multiplied by these funny units of resistance. Coulomb squared gets canceled. We have seconds in the numerator, seconds squared in the denominator, and we're just left with joules per second. All right, how might we use that equation? An interesting example I came across as I was trying to remodel my bathroom was we were going to add a steam shower to the bathroom, where you have this steam generator that pumps steam into the shower. And this had to be connected to the service panel behind the house, and it was about 20 feet away. I knew that it was a 6 kilowatt generator, 6,000 watts, and I was going to plug it into 240 volts. That was the service panel. So I went to the local hardware store, and they had this chart up on the wall to tell me what size of wire I needed. Well, I needed to know the current and the distance. I knew the power and the voltage, but I didn't know the current. I asked the guy at the hardware store to help me. Couldn't help me. So I had to think about it myself, and fortunately I was able to remember that power equals voltage times current. That 6,000 watts of power connected to 240 volts is going to be about 25 amps. So you have the current, which fell within that range, the distance, which fell within that range. So an 8 gauge wire is what I purchased. And a lot of students like guess and check. So maybe you had guessed a 10 gauge wire, and you plug this in, and then you turn it on, and the wire gets too hot and burns down your home. So maybe guess and check wouldn't be the best method there. All right, so now that we've talked about what gauge wire to use, let's see if we can understand what variables affect how much resistance a wire has. So we're going to fall back onto our analogy with electrons flowing through a wire, analogous to water flowing through a pipe. So the question here is, which pipe would have the most resistance, or another word for resistance is impedance, to hinder or to impede, to transporting a quantity of water. So if we had a pipe this long and a pipe twice as long, maybe no surprise, length is going to be one of the variables that affects how much resistance there is to water flowing through there. And is it directly proportional or inversely proportional? Well, the longer the pipe, you might guess, would have more resistance. In fact, twice as long would have twice the resistance. Both variables went up, so that would be directly proportional. And then now we have a variety of different size pipes. So which of these pipes would have more resistance to transporting a quantity of water? And they're different sizes, but is it the diameter, the radius, the circumference, or the cross-sectional area? So if I look at, say, these two pipes here, if this pipe here was twice the diameter of this pipe, would it have twice as much resistance or half as much resistance? That's what it would be if it was a variable related to the diameter, the radius, or the circumference. Turns out it's going to be related to the cross-sectional area, because if this had twice the diameter, it would actually have 4 times the area of this one. And 4 times the area is going to make it a lot easier to transport water through that. 4 times the area would actually make it have 1/4 as much resistance. So directly proportional or inversely proportional, when one variable went up, the other variable went down, and that would make it inversely proportional. The last variable that affects how much resistance a wire has is what's inside the wire, what the wire is made up of. Now, if you fill both these pipes with, say, small marbles or large marbles, water can still make it through there, but it's going to be greatly impeded. I think that water would be able to go through this one easier because the gap in between the marbles is larger. So that brings us to this concept called resistivity. And resistivity is not the same thing as resistance. It's a property of the wire itself. What the wire is made up of, how easily electrons can flow through that type of metal. We do use the Greek letter rho to abbreviate resistivity. Now, we did use rho for another concept, which was density, mass divided by volume, but it's not the same thing. We just use the same letter. Okay, so we put those variables together, that resistance is directly proportional to the length. resistance is inversely proportional to the area. And then we have the resistivity. You could think of that as just being a proportionality constant that turns meters and square meters into ohms. So resistivity is going to be measured in ohm meters. Because if this is measured in meters and this is square meters, they cancel and we're left with meters in the denominator. So this would have to have meters in it so they cancel, and would also have to have ohms in it so it didn't cancel, and left with ohms as our result. And you can look up in a table what different materials are and how much resistivity those materials have. You can also look up in a table what gauge of wire you have, and most homes use about 14 gauge wire. In the kitchen and in the bathroom, they often use 12 gauge wire. It's a little bit bigger wire to handle more current. But knowing the gauge, you can find the area. Because the resistivity here was measured, had meters in it, we would have to make sure that we found the area in meters. This is the diameter, but from the diameter and pi r squared, you can calculate the area. All right, we looked at resistance through a wire. Now we're going to look at resistance of these tiny little devices, and they're called resistors. They have color codes on them. So let me talk first of all what those things are on the inside. Wire comes in, wire stops, new wire goes out, and the ends of those wires are separated by some length. And then inside that, where the electricity flows through, has some cross-sectional area, and it's made out of often carbon, which has a particular resistivity. So the play of those three variables determine how much resistance one of these tiny little resistors have. And if you open up a circuit board, these resistors can be very small. So small that if you try to type a value for the amount of resistance they provide, the number would be so small it would be hard to read. So we have this universal color code here. First thing we need to see is that usually, always, you'll find a gold stripe on here, and it's going to be metallic, so it should be able to be easily seen as being gold. But gold is the 5% tolerance, that whatever number that we measure here, the plus or minus value would be 5% of that. So if I find the gold stripe, we go to the other side to find the first stripe. It's yellow. Yellow stands for 4. Violet stands for 7. Black stands for 0. The first two numbers are the digits. You don't multiply those together, they're just digits. So the 4 and the 7 make 47. The third stripe is 0, and that's what 10 gets raised to the power 2. So 10 to the 0 it results in just the number 1. So this manufacturer says that if we were to measure this, we should measure 47 ohms, give or take 5% of 47. And 5% of 47 is 2.4. So if we were to measure this with a multimeter, the manufacturer who made this says we should measure 47, give or take 0.24 ohms of resistance. We'll practice that one more time here. Again, we see the gold stripe here, so that's the last stripe. The first stripe here is brown, and brown is 1. Green is 5, red is 2. So the first two are digits, that's 15. The third stripe is the number 2, so we have 10 raised to the power of 2, which is 100. 15 times 100 is 1500. The gold stripe here is 5%, so that's 5% of 1500, and that's 75. So the manufacturer here says that we should get 1500 ohms of resistance within a range of plus or minus 75 ohms. And these resistors are used in circuits to get the right amount of current running through different parts of the circuit. So that's a little introduction to Ohm's Law, the resistance of a wire, the resistance of these little resistors.